Hi, I did a brief unboxing of this UT8805E 5.5 digit bench meter in the last video, and this time let's take a deeper dive and look at what it has to offer. And by the way, UNI-T provided me this unit for me to review, and I will provide the link in the video description below for those who are interested. As a refresher, the UT8805E is a lab-grade 5.5 digit bench meter which has an impressive 1-year DC accuracy of 0.015%. For DC voltage measurement under 20 volts, the input impedance is over 10 gigohm. For comparison, the input impedance of your typical multimeter is usually at around 10 megohm. And the benefit of this high input impedance is that it minimizes the burden on the circuit under measurement, and therefore should give you a more accurate measurement result. Anyway, let me power it on and show you some of the features of this UT8805E. As you can see here, the unit boots up relatively quickly, and this is important as I have mentioned again and again in my reviews of other products. As for an end user, especially for casual use, the faster the boot up time, the more likely the instrument will be used more often. Anyway, it boots into DC voltage measurement mode by default, and you can change the measurement modes using the buttons up here. For example, right now we change it to AC voltage measurement, and we're going back to DC voltage measurement. Also by default, the display update rate is set to slow, which corresponds to roughly 3 times per second, but you can easily adjust it to medium or fast, and the update rate would change to 10 and 5000 accordingly. So let me show you here. So if I press this and I press medium, it will be updating at roughly 10 times per second, and I can change it to fast, and obviously the update rate is much faster here. So let's change it back to slow here. And also you can see that the display is jumping around quite a bit, just like what we observed in our initial unboxing video. And that is because we have extremely high input impedance. In this instance is at 10 gigohm. And by the way, the stock leads are high quality ones. The cables are very soft here, as you can see. Now, not sure how well it shows on the camera here, but according to the print on the wire, it has a 16 gauge core and is rated to withstand 6000 volts. Now, one thing disappointing is that the tips of these probes are not gold plated. The ones from my UNI-T UT8805E Plus, for example, these are gold plated, as you can see. So this is definitely a little bit disappointing considering this is a lab grade meter. So the first thing I thought I would do is to verify its DC measurement range accuracy. After all, this is a 5.5 digit meter. Now, in my lab, I have a DC voltage standard, the EDC MV216, and that should be able to verify the accuracy of this bench meter. Anticipating this test, I have left the MV216, the voltage standard, on for the past few days, so its output should have been stabilized. Right now you do see a little bit of offset when output is at 0, and that offset is roughly 2 microvolts. Now we can go ahead and route it out so we can reduce the noise here. So let's do that. So now the output is at exactly 0. Now let me set the output to 1 millivolt and see what we got on this display. And you can see it's exactly 1 millivolt. And let's just cycle it through for a few to get a sense here. 2, 3, 4, 5. You can see that we're pretty much displaying the exact output. 6, 7, 8, 9, 10. So this is the millivolt range of the MV216 output, and let me change it to the volt range and we'll repeat the measurement here. So let me change it to the volt range. Let me turn it off, change it to volt, of course. Let me clear the relative measurement here. Alright, now I have route out the last significant digit again, and there is some variation there, but for all intents and purposes, it doesn't really matter. So let's increment the output to 100 millivolts. And you can see essentially we are at exact 100 millivolts. And let's go to 200. 3, 4. You probably noticed that we lost a digit when we crossed that 200 millivolts, and that's because this is actually a 200,000 counts meter. So just want to point that out. And now the output is at 400 millivolts. So let's go to 5, 6, 7, 8, 9, and finally 1 volt. As we have demonstrated, the DC measurement range is extremely accurate and stable. Next, let's take a look at the AC voltage measurement range. So let's switch to AC measurement here. And let me get rid of the input here. And by the way, for many ranges on this meter, you have the ability to specify a secondary display. So for the AC voltage measurement, you can also display the frequency. Let me show you that. So I press dual, and you can see here we have the ability to display the frequency. So actually, let's leave it as this and take a look at the mains voltage measurement. So let me put this in the socket here. Give me 1 second. And you can see currently the voltage reading from the mains output is at 120 volts, roughly 60 Hertz exact. According to the manual, the AC voltage measurement bandwidth can go up all the way to 100 kHz. Let's actually verify that with a function generator. And for that, I'm using my UT-UT8805E. You can see here, that's generating an output currently at 1 kHz, 1 volt RMS. And we're measuring that signal here on this multimeter. So let me go ahead and increase the frequency here. So right now we're at 1 kHz. As you can see, the reading out here is roughly 1 kHz. And let's go up to 10 kHz here. You can see the output remains at 1 volt. And let's go ahead and increase it further to 100 kHz. And you can see that we're still getting that 1 volt reading. So let's actually try to push the output frequency a little bit more. Let's do 200 kHz. And just to remind you, right now the input frequency is actually twice the limit as what is specified in the manual. But you can see that we're still getting that 1 volt reading here. So let's actually increase it to 300. Wow, that's actually pretty impressive. 4, 5, 6. Now we did see that the measured voltage started to roll off a little bit, but it is still within that 3 dB limit. So let's keep increasing. 7, 8, 9, 1 megahertz. And you can see even at 1 megahertz, we're still within that 0.707 limit. So 1.1, 1.2, 1.3. As you can see here, we have already exceeded the maximum measurable frequency range, but we are still getting the voltage reading within that 3 dB bandwidth limit. So what I can say here is that the 100 kHz bandwidth claim is actually very conservative, as right now we're already at 1.3 megahertz. By the way, in pretty much any setting, you can also invoke the mathematical functions. And let me show you here actually. So if I press math, you can see that we have a bunch of other sub options here. So one of which is statistics. We can enable that, for example, and you can see that this gives you the measurement statistics from the average, the standard deviation, and whatnot. And that actually can be very useful in terms of measurement. Of course, we're not going to get into details here, but nevertheless, I just want to show you the functionality here. Anyway, so that was that. And what else? We can set the limit and high and low. And this is mainly used for testing, as you can set the beeper on and off, depends on whether or not the readings have exceeded the limit. And of course, you can change the measurement to decibels and relative. And another function potentially going to be useful is this display option. To better illustrate the display options here, I have updated the output from the UT-G962E to a square wave, and currently is at 0.1 Hertz. So let's actually take a look at that. So if I change it to trend, let's observe the measured signal. And by the way, I have also changed the range to DC so that we can capture the signal here. So you can see that we are actually seeing that square wave being drawn on the display here. Now I have let it running for a while, and you can see that we essentially captured the waveform of the input signal. Anyway, so let's change it to, let's say, the display to bar display. I played around with this bar graph a little bit, and I can see that the update speed is actually not great. Right now I have changed the input signal to a sinusoidal back again at 0.1 Hertz, and you can see that the update rate between the number display and the bar graph is essentially the same. So this is actually not going to be that useful, in my opinion. Ideally, the bar graph display should be updating at a much faster rate. Now, let's see if that is actually related to the update rate in general. So let's see how we can do this. Let's go back to update speed. Let's do medium. Yep, you can see that the bar graph update rate is essentially tied to the display update rate. So in my opinion, the bar graph update should be faster than the display, and that would make it much more useful. And let's take a look at what else we get. We've got, okay, so there's also a histogram option. And I suppose this would be useful if you are binning your components, for example, measuring your resistors and to see the distribution of the values. Anyway, so these are some of the display mathematical functions here. So let's get back to number. And also you can see we can change the display output from voltage to dBm. And this will definitely come in handy when you are measuring some power measurement. Anyway, so let's change it back to voltage. Now I'm measuring the current output from my 100 microamp current standard. You can see that the readings on the UT8805E is at 99.987, so which is very close. Now, for comparison, I have also did the same measurement on my Keithley 196. You can see up there, that's a 6.5 digit meter, and the measurement is 99.995. So give or take, both meters are essentially measuring the same output here. And if you were in AC current measurement mode, you also get an option to display the source frequency as a second parameter. Now let's take a look at the resistance measurement mode. As a bench meter, it supports both 2-wire and 4-wire measurements. Let's first take a look at the 2-wire measurement. So for that, I'm changing it to resistance measurement mode. And let's zero it out. And you can hear it auto-ranging the relay clicking here. And now we do have some residual resistance, and we can zero it out. Let's try and measure a 1K resistor here. And you did hear the relay clicking. It took about a second for the result to stabilize. And that's actually pretty quick for the auto-ranging. So no issue at all here. Of course, you can always change the display speed to fast, slow, and medium, and right now we're at slow, so roughly 3 times per second in terms of the measurement. For low resistance, 4-wire measurement is actually preferred, as it eliminates the lead resistance from the measurement results. So actually, let's take a look here. For 4-wire measurements, we need to use Kelvin clips, like what I have here. Of course, these are not included with this meter, but you will need these if you're doing 4-wire measurements. So let's actually first switch to, let's actually first plug it in. And this is the common leads here. Okay, so let's switch it to 4-wire, shift, and ohm measurement. Now we're in the 4-wire measurement mode. And just to verify, let's short the leads here. So ideally we should get a 0 reading. And you can see that that's pretty close. Of course you can always round it off, but let's keep it as is. And for this measurement, I have a 100 ohm precision resistor here. This one has a 0.1% tolerance. So let's give it a go. And you can see that the measured result is 99.968, which is pretty much the actual nominal reading of that resistor. And now let's take a look at a capacitance measurement. And for that, again, I'm going to change the leads here. And I'm going to swap in these stock alligator clips, as we can clip onto the capacitors. Let's switch to capacitance measurement mode. And by the way, in this mode, according to the manual, we only have 3.5 digit resolution, and the maximum capacitance we can measure is only up to 2000 microfarads. So the first capacitor we're measuring, let's take a look. We have a 22 microfarads capacitor, and let's give it a go. And there are going to be some lead capacitance here, but let's see here. Okay, that's actually pretty good. Right now we're reading 0.02 nanofarads, which is 20 microfarads. The next capacitor we're measuring here is this 100 nanofarads one, and this one we know from previous measurements is a little bit on the low side. I think it's only 85, 86 nanofarads, so just keep that in mind. Let's give it a go. Yep, you can see that this is roughly in line with what we had before. So now let's move on to a few slightly larger capacitors. The next one I'm going to measure is this 22 microfarads one. And as you can see, the measurement speed is actually not that fast. It's actually pretty slow. It took a few seconds before it finalized the reading here. So this is a 22 microfarads capacitor. And the next one, finally, I'm going to measure one that is a little bit larger. Let's see here. This one is a 1 millifarads, 1000 microfarads one. So let's take a look. And it's taking considerably longer. Wow. So as you just saw, it took quite a few seconds for the reading to stabilize and reach this final 1 millifarad reading. Now, to be very honest with you, I think the capacitance measurement mode on this UT8805E is a little bit underwhelming, as it, first of all, the maximum measurement range is only up to 2 millifarads, and also it's just very slow. The maximum resolution is only at 3.5 digit, so there's nothing special about it. All right, next I think we'll take a look at the temperature measurement mode here. So now we're in temperature measurement mode, and this range is worth exploring a little bit as it supports many different types of temperature sensors. So for example, if we come here to the probe setting, you can see that currently is set as resistance temperature detector 2-wire. But if you take a look here, we have the option of RTD 4-wire, thermistor 2-wire, thermistor 4-wire, and thermocouple. And for the thermocouple, you can see we also have a lot of different options with different thermocouple types. So sorry about that. Let's come back here. For example, type J, type K, all the different thermocouples that you would expect. They're all supported here. So let's come to, let me see, how do I get back here? Is probe type. Let's come back to thermistor, as right now we have these clips on, and I do want to take a look at the thermistor here. So I have a standard thermistor that we can connect. And of course, the reading is not very accurate right now, but one thing I want to show you though is in this mode, you can actually display a separate parameter here, dual display, and you can choose sensor, and now it actually tells you the resistance value, so which is very cool. Of course, you can also change the unit to Fahrenheit and whatnot. Definitely right now, I think this is a little bit off, as the temperature in the lab is definitely much higher than 40 degrees, but nevertheless, let's put my hand on it. You can see that we can actually measure the temperature, and at the same time, you can see the resistant value changes. So now I think this may be because the thermistor we used is probably not really the standard one that it calls for. That's why you are seeing this discrepancy in the measurement value. But nevertheless, you have the option to use a thermistor for temperature measurement. So that's the first thing I want to show you. And the next thing I want to show you is using the stock thermocouple that is supplied with the unit here. So let's come back here and let's probe setting and change it to thermocouple, and I think this is a K couple, and we will plug it in. So now you can see this is the temperature measured by the thermocouple, and as you can see here in temperature measurement mode, the resolution actually we have 0.01 degree, which is excellent. And also we have a secondary display even for thermocouples. Let's take a look at what that secondary display is. By the look of it, you can display the sensors. What is it reading? Okay, so millivolt. Let's come back here to see what else. You can display the reference temperature. I assume that's the internal temperature reference. Anyway, so that's the secondary display here. Alright, so I think next let's take a look at the continuity here. So I'm going to unplug the thermocouple here and plug back in the leads. So let's change it to continuity. And by the look of it, you can have the beeper either on or off. Right now it's on. Let's take a look. The response time is definitely very fast, and you can also see it from the update. Now, the measurement doesn't seem to be latched, as you can hear the scratchy sound when I touch the probes. Now, some people prefer latched continuity tests, and some people prefer unlatched. I personally don't really care as long as the reaction is fast, which is definitely the case with this meter. Now let's take a look at the diode test. So for that, the first one is a silicon diode, and let's take a look here. And you can see that we can measure the forward voltage drop, no problem. And let's bring in an LED here. Let's see if we have a red LED. Yep, we do. And you can see that we are also able to measure the forward voltage drop. How about a white LED? And this is a white LED here. Let's see the other way around. You can see the LED is lit, but we are not able to measure the voltage. According to the manual, I think the output voltage in ohm measurement range and in diode measurement range is roughly 8 volts. So let's actually verify that. Let's see here. Yep, as you can see, is 8.6. So that's pretty much the spec voltage output. So I'm a little surprised actually it's not able to display the forward voltage drop for a white LED, as it's well within this output voltage limit. So let's take a look again. Yeah, as you can see, the LED is lit up, but we don't get the voltage display. That is a little bit disappointing in my opinion. This bench meter also supports frequency measurement, and we just switch it to frequency period measurement here, as you can see. Now I'm inputting a signal from my UTG-962E, which is 1 kHz, and you can see we measure that with no problem. So this meter, technically speaking, can be used as a frequency counter for low frequencies. Let's actually increase the frequency and see if we are able to measure it at any higher frequencies here. So this 10 kHz. No problem, and 100 kHz shouldn't be any problem either. And by the way, you can also enable a secondary display here, so let's do that. You can, in this case, do either the AC voltage, and right now we're at 1 volt, or you can select the period here, so that's actually coming in quite handy. Anyway, so we're currently at 100 kHz, and I would expect this frequency can go up quite a bit, even though the specified, I think, maximum is 100 kHz. But let's do 200. Yeah, you can see no problem. 300, 4, 5, 6, 7, 8, 9, 1 megahertz, 1.1, 1.2, 1.3. Yep. So similar to what we had before, it seems that the maximum it can display is at 1.2 megahertz. And that's pretty much everything I wanted to show you about this UT8805E bench meter. The capacitance measurement mode has a bit more to be desired, but overall it is a very capable 5.5-digit multimeter. I didn't cover in this video, but this meter can also be remotely controlled by either USB or RS-232 with skippy command. Anyway, I hope you enjoyed this video. If you liked the video, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will catch up with you next time.